Hello, in this video is chapter 6 section 2, our second video, and here we are determining the inverse of a function defined by a map or set of ordered pairs. So let's define what an inverse actually is. Suppose that f is a one-to-one function, then corresponding to each x in the domain of f, then there is exactly one y in the range because it's a function. Remember, that's what functions are. Each x corresponds to one y. And corresponding to each y in the range, there's exactly one x in the domain. Where I was that is because it's one-to-one. So to paraphrase that sentence is a function must be one-to-one. You're going to let the function to be one-to-one, and it's a function. Okay? So then what we're going to say is their correspondence of a range of f back to the domain of f is called the inverse function. All right? The symbol f to the negative 1, which we read it as f inverse, or the inverse of f, and used to denote the inverse function of f. Okay? Now let me kind of paraphrase why that's actually true. Okay? You remember, to be a function, every x goes to exactly one y. But in order for it to be one-to-one, every y has one input value going to it. And the reason that's got to be one-to-one is because the inverse has the mapping going the other direction. So, in other words, if 1 goes to 2 and 3 goes to 4 and 5 goes to 6, then the 2 goes back to 1, the 4 goes back to the 3, and the 6 goes back to the 5. That's how the mapping works. It works the other way. So in essence, what you're doing is all the inputs are now outputs, and all the outputs on the original function are now the inputs. So if a gives me b in the function, and that function is one-to-one, then b will give me the a in the inverse concept. So in other words, all the mappings are in reverse. So if you have a list of ordered pairs, and you want to know what the inverse of that in one-to-one function is all you got to do is switch the ordered pairs. So if 1, 2 is an ordered pair, then 2, 1 will be an inverse function's point. If 3, 4 is a point on the original function, then 4, 3 will be a point on the inverse. If 5, 6 is a point on the function, then 6, 5 is a point on the inverse. So like I said, what was in the domain is now a range element for the inverse. What was the range element in the function is now a domain element in the inverse. So that's kind of how it works. So let's look at this. Let's look at an example here. We're going to finding the inverse function defined. Okay, so we have the inverse defined by a list of ordered pairs. This is kind of what I was discussing a while ago. So we have negative 3, negative 27, negative 2, negative 8, negative 1, negative 1, 0, 0, 1, 1, 2, 8, and 3, 27. Notice the function is one-to-one. There are no repeated y coordinates, and it is a function because there's no repeated x coordinates. Okay? So state the domain and the range of the function and its inverse. Okay? So let's get started on this one. So the inverse of the given function is found by interchanging the entries in each ordered pair. So it gives me negative 27, negative 3, negative 8, negative 2, negative 1, 0, 0, 1, 1, 8, 2, 27, 3. Now notice there are a couple of those ordered pairs that are identical to the ordered pairs in the original function. That's okay because it's still one-to-one. Okay? Now, that's the inverse function. So the first set of ordered pairs, the given set of ordered pairs is a function, and it's one-to-one. And when I switch them, then it becomes the inverse function. Then they want me to do is determine what the domain of the function is. So those are the x coordinates. So it's negative 3, negative 2, negative 1, 0, 1, 2, 3. And the range of the function is negative 27, negative 8, negative 1, 0, 1, 8, 27. So those are the outputs. That's the original function. Now the domain of the inverse function is negative 27, negative 8, negative 1, 0, 1, 8, and 27. And you can get that from the answer, or you can also get that from looking at the domain, looking at the range of the given function. If you notice, the range of the inverse, this is important, the range of the inverse is the domain of the function itself. And the domain of the inverse is the range of the given function. So now what I'm hoping is you guys will see why it wasn't important to have the function being one-to-one. Think about it. If the function isn't one-to-one, that means there is a repeated y coordinate for two different inputs. So 2 could go to 3 and 5 could go to 3. That's for a function not being one-to-one. So 2 could go to 3, 5, and it's still a function. It's still a function. But when you switch them, the 3 would have to go back to the 2 and 3 would have to go back to the 5. And that causes a problem. Why? Because it wouldn't be a function then. So you can't have an inverse function if it's not a function to begin with. Okay? So that's why it has to be one-to-one, because one-to-oneness means there's no repeated y's. Okay? And the reason that has to be is because when you turn them around, you'd have a repeated x, because when you turn them around, you have an x coordinate that's going to be repeated. And remember, to be a function, it has to be, every x has to go to one y. But if you're allowing the function not to be one-to-one, and you start turning them around, you will have an ordered pair that is repeated, because to function that is not one-to-one will have a repeated y value. So that's kind of how, that's the reason a function has to be one-to-one in order to have an inverse. So, but the procedure is pretty simple when it's given to you as a mapping. So all you got to do is switch the ordered pairs. And if you notice, f to the f inverse of f of x equals x, where f is a domain element, and f inverse of x is equal to x, where x is the domain element of the inverse. So basically, what they're basically saying is they kind of cancel each other out. But why it cancels each other out is because of this. If 2 goes to 5 in the function, what will 5 go to into the inverse? Well, go back to 2. Well, that's what you started with. If a goes to b in the function, and a is what you started with, what will b go to in the inverse? It'll go back to a, right? Well, that's what you started with. So that's why f inverse of f of x equals x. It's what you started with. And it works the same way too. If you put x over here in the inverse function and you come over here to a domain element here into its range, well, that now is a domain element of the function. Where is it going to go? Back to the x. It's going to go back to where you started at. So that's why you think of it as it's being canceled out. Let's look at a picture of that, what's going on. See them? There's the picture. That describes it really well. Look at the pink. That's where you start with. It goes to an element in the blue in the function. And then you apply it back to the inverse. Where does it go back? To the same point in that domain. So, and then when I said this a while ago, the domain of f is the same as the range of the inverse function. And the range of the function is the same thing as the domain of the inverse. So, sometimes they try to trick you. They will ask you what the range is on one function, but they don't give you what that function is. They give you the other one. So, well, if I'm asking you for the range of the inverse function, and I give you the function itself, well, what do you have to do to find the range of the inverse function? Well, you'll need to find the domain of the given function. So finding the domain of the given function is equivalent to finding the range of the inverse function. And sometimes they try to trick you with doing that. They'll give you one of the functions and ask for the domain or the range of the other. So all you have to do is find the domain or range and switch them around to answer that question. Sure, you can, if they ask for the domain of the inverse, you could actually find it by a technique what we either talked about or we will talk about, and then do it that way. And you can, and it works, but it's a little bit few extra steps. So another picture. If x is an element of f and it goes to fx equals 2x, then the inverse is going to be 1/2 x. And we'll talk more about that later, okay, why that's true. But to put that back in, 1/2 of x goes back to the same thing, what you started with, x. Okay? All right. Now, here we're going to do is we're going to verify functions are inverses of each other. Okay? How do you do that? This is called the theorem of inverses. So what we're going to do is we're going to do f inverse of x, and it has to be the x, and then f inverse of f of x is equal to x, which is right above at the very top. So that has to be true in order for it to be an inverse. So f of x is 1 over x minus 1, and f inverse of x is 1 over x plus 1. For what value of x is f inverse of f of x equals x? For what value is that? So let's look at that. So the domain of f is x not equal to 1, and the domain of the inverse function is x not equal to 0, because you cannot divide by 0 on the second one, you cannot divide by 0 on the other neither, because it's going to be 1 minus 1 if you make it x equals 1. So now let's look at this. We have f of f inverse of x, so we plug in 1 over x minus 1 for the function, because that's what it equals. So we did this in compositions back in 6.1. So 1 over x minus 1 plus 1. So you flip that over, you'll get x minus 1, and then plus your 1 again. And those cancel, leaving me with just x. So that's halfway there. Now we're going to do f of f inverse. F of f inverse of x equals f of 1 over x plus 1, so we substitute that in. So it's 1 over input minus 1. What is input? The number in the pink, 1 over x plus 1. So 1 over x plus 1 minus 1, the ones cancel. And you'll get 1 over x. And if you flip them and multiply them, you'll get x, provided x does not equal to 0. So both of them equals x both ways, as long as x meets those restrictions. So therefore, these two functions are 1-to-1. Now what does that mean? Well, that means if I have AB working for the original function, then I'm guaranteed that BA is going to work for the inverse. Let's give you an example. Let's put a number in the top function. Let's put in 0 in the original function, f of x. Let's put in 0. If we put in 0, we get 1 over 0 minus 1. Well, 1 over 0 minus 1 is negative 1. That is its output. But look what happens when I put negative 1 back into the inverse. So 1 over negative 1 is negative 1, and what's negative 1 plus 1? Yep, it's 0. Because 0 gave me negative 1 in the original function, but in the inverse, negative 1 gave me 0. It switches. So if A gives me B in the function, then B gives me A in the inverse. That's the whole point of inverse functions. It allows you to switch all the inputs and outputs around, which is pretty cool. I mean, if I gave you a function and listed all the ordered pairs and say, hey, I want you to come up with a function that will make all these ordered pairs switch, okay? And if without knowing what an inverse is, then you can't do it. So, and we will, by the time we leave this chapter, this section, we will be able to do that, okay? So right here, they gave you what the functions are. Before this is over with, we're going to be able to find what the inverse is ourselves without them telling me what it is. But this is how you prove two functions are inverses. And you're like, well, what if they're not inverses? What would happen? They won't equal to x. So if you're saying, here's two functions, are they inverses? If you tried this technique on two functions that are not inverses of each other, something, or probably both of them, one or both will not give you x. Okay, so that would be the problem with functions that are not 1-to-1. But these, they set it up. They knew they were 1-to-1 to begin with. Okay, so that concludes this video. Our next video, we'll be talking about obtaining the graph of the inverse function from the graph of the function. So they're going to give us a graph, and we're going to know it's 1-to-1 by looking at it by the horizontal line test. And then based on that graph, we're going to look at the graph of its inverse. Okay? But that concludes this video. If you have any questions on it, you let me know. And as always, you have a good day.